Hello, my name is Juan Pablo Speer,
Hi, I'm David Jin.
and we're going to be presenting our work on laminar chaos, which can be found in variable time delay systems.
So the first question is, what is a laminar chaos? So it's a nearly behavior in chaotic systems which discovered in last year by Mueller, Otto, and Roudens. And here's their experimental simulations, theoretical simulation in their paper. So there are two characteristics of laminar chaos. The first is a steady phases, which we can also call the laminar cases. It's a steady, if it's a flat in each phases, we can zoom in and see it show over all through these all time traces. The other one, the characteristics is the short irregular burst like transitions, which we can find as a vertical that separated these two laminar phases which are flat. They appear throughout the time series.
So Michael Mackey and Leon Glass are mathematical physiologists who wanted to study the density of white blood cells in the bloodstream. They published their findings in 1977, and they also included something called the Mackey-Glass equation, which is a nonlinear time-delay differential equation. And it's been shown to display a range of periodic and chaotic dynamics, and was also used in a 2012 thesis for the first hardware implementation of reservoir computing. So here we have the equation on the bottom, and we're going to break it up into its components. And there's our simplified schematic of our circuit. So on the far right-hand side of the equation, that's a nonlinearity term. And that corresponds to a nonlinear device, which is made up of two junction field effect transistors, or JFET transistors. And they use electric fields to control the amount of current that's flowing through them. And then we have a gain device, which corresponds to the A parameter. And that controls the round-trip gain of our system. It's made up of an operational amplifier and a potentiometer. And here we have one of the most important parts of our system, which is the time delay. You can see in the equation that it's a constant, but we can modify our system so that it's variable in time. And we also have a low-pass filter, which attenuates signals above a certain frequency, and that frequency is determined by the filtering time constant.
So after looking at how the functional schematic look like, we're going to look more into our experimental setup. So we keep nonlinear device and gain device still in the analog circuit separately, but we want to merge the filtering and the time delay implemented with the Arduino board. And that's our experiment setup. And above is analog circuit, and below is the Arduino DU board. They are connected to form a loop.
So the Arduino board imports data from the analog circuit, and using an analog to digital converter, it holds the data for 40 milliseconds in our case, and then feeds it back into the circuit. And what we can do is we can implement a variable time delay by feeding a voltage signal into the Arduino, and the Arduino will digitize that signal and use it to change the indexes of the data array that is holding the analog circuit data. And so if we vary the voltage signal, then we can vary the time delay.
So the first thing we test out of our system is the nonlinearity, since it's a very important component for chaotic behaviors. So we use the x input versus x output, we're showing the black box, that derived from the Mackey-Glass equation to fit our experimental measurements. So then we can approximate Mackey-Glass nonlinearity, and also we can get the parameters we can use for simulations to compare with our experimental data in the further studies.
So using the parameters that we found in the last slide, we were able to simulate what our system would do under a constant time delay of 40 milliseconds. And you can see that as you go down and you increase the gain, you find stable, periodic, and full turbulent chaos.
So since the constant time delay systems are well documented in studies, we want something more interesting. So we variable our time delay. The way we implement this we change our time delay into a sinusoidal wave. Its offset is a mean time delay of 25.2 milliseconds. We're showing the graph. The purple is our sinusoidal wave. And the amplitude is 0.9 over 2 pi. And TD is the period of delay signal modulation, which is the frequency is 1 kilohertz. So these kind of, the combination of this sinusoidal with our system can induce laminar chaos, which will show more comparison in the future.
So here we show the first experimentally observed instance of laminar chaos. And you can see that it compares very well to our simulation, with the period of the laminar phases being 2 times the mean time delay. And here we compare it with a case of turbulent chaos, which you can see is very chaotic, its shapes are everywhere, whereas laminar chaos is very structured along the x-axis and chaotic along the y-axis.
So after looking at these visual comparisons, we want to look into more intuitive way to show how different are these. So I want to show them some audio. The first is a 440 hertz pure sinusoidal wave with an A sound. So we can notice it's a very pure sound. So let's hear about this. So the first one we'll look at is a periodic wave with a constant time delay. It looks like a sinusoidal. So let's hear about it. So we can still hear it's kind of pure, but it's not as pure as before. Then let's look at the periodic with a variable time delay, which looks like a squarish type of wave. Okay, here clearly there's a little more noise than before, but it's still kind of pure, but not as pure as before. Now let's look at the laminar chaos, which has a square and they have steady phases separated by the burst transitions. It's very clear. It's like we can hear the steps between inside this audio. But let's look at the most naughty, chaotic behaviors here. That's very obvious. This is a very noisy wave compared to the laminar chaos, and we can demonstrate the difference from these comparisons from audio.
So in conclusion, we were able to observe laminar chaos in a Mackey glass feedback circuit with variable time delay. We demonstrated both turbulent and laminar chaos, both in simulations and experiments, and we were able to construct a Mackey glass system that uniquely utilizes an Arduino board and is suitable for university labs. Thank you for your attention.
Thank you.